Thanks for the introduction, and thanks for not just having a blank slot in the program and giving me the opportunity to speak to you today. This will probably be, I'm going to speak about some of the collaborative work we do at Sussex, which is here. You can see the university campus surrounded by a national park, Seven Sisters over here, and Brighton and Hove in the background. In materials physics, we're mainly interested in let's say very much more applied physics than most of the talks this morning have been. So let me give you a flavor of what we're doing and where some of the challenges still are in this area. So we're mostly interested in nanomaterial networks. That is predominantly particulate networks of nanomaterials that can be perhaps silver nanowires, graphene, carbon nanotubes, materials like these, whether that's thin films or macroscopic assemblies of emulsions, perhaps. And the main interest here is that these allow us to tune properties of the system. We can interface with the system. We can change the connectivity of the system. We can make heterostructures. We can change the chemistry and interface with them in various ways to ideally generate new functionalities of some kind. And the main interest in that is we can then scale these things up to make macroscopic sensors, for example, or this is actually conducting AFM images, so we can map current paths in these systems. So we're looking at very applied properties of these systems. And because we keep the processing very simple and scalable, we can tune the processing on demand, and we can tune the kind of systems that we can make for sensors, for energy applications on component. And we're working with various industrial partners. We're predominantly industrially funded working in this area. Okay, so the materials I'm going to talk about today are nanosheets, are 2D materials, graphene and molybdenum disulfide specifically. We prepare these by exfoliating from bulk crystals such as graphite, using ultrasound and a carefully chosen or selected combination of solvents, surfactants based on surface tension matching and Hansen parameter, Hansen solubility parameter. I will add, I'm a physicist. I've done materials work for a while now. Most physicists think we're chemists, so I won't be offended if it feels the same. By choosing either surfactant solutions, so amphiphiles, soap molecules, or appropriate solvents, we can disperse these nanosheets from bulk crystals into dispersions which look like something like an ink, right? We have lots of nanosheets floating around, relatively stable, not fully colloidally stable, but kinetically stabilized in these dispersions, and we can then do lots of things with these. This sort of crude simplified Venn diagram is using this technique, which is known as liquid phase exfoliation, LPE. Just to put into some context, we believe we produce defect-free nanosheets of relative high electronic quality, and hopefully you'll see that from some of the results later. So similar to Scotch tape in the Scotch tape method in that sense. But it's more scalable and much more low cost than chemical vapor deposition or reduction of graphene oxide, or even potentially electrochemical exfoliation, which is a new technique developed in this area. So we can do it with graphene, but we can also do it with molybdenum disulfide, boron nitride, or any one of clicking the wrong button, any one of a range of materials that we exfoliate in our lab. And these have various interesting functionalities, lots of high K materials, lots of electrochemically active materials, some thermoelectrics, which I'll mention again later. And we're now producing these at scale in a pilot scale in a liters to kilo scale process that uses high pressure homogenization to produce these nanosheets in large quantities. And the main advantage for us there is it's allowing us to make measurements that are not possible when we're working at microgram scale. That allows us then to do things like print these, and this is printed with a domestic inkjet printer, graphene electrodes, and molybdenum disulfide in the channel. So it just gives you an idea of the simplicity of the processing and the sort of versatility that we hope to have. And when we go in with the AFM and look at what these networks look like, they are locally very disordered. So we heard about single crystals and polycrystalline materials. These are another extreme or the next level of disorder in these systems. They're particulates. They have junctions between them that I'll talk about. Those affect the behaviors. But over longer length scales, they're actually quite uniform, or the disorder repeats over. So we can start to understand the properties of these ensembles. What we decided to do, because I've got as much graphene fatigue as anyone, probably more. And what we decided to do was actually look at some of these systems and say, okay, so we can make graphene, and it's quite well known that you can make graphene by this technique. And you can prove that there are single layers in there, but do they actually have to be single layers? I mean, there's a lot of backsliding in the literature in our field as well, where people will quite happily use various grades of graphenes, and they're not actually studying any emergent properties of any kind from the exfoliation. So with our pilot scale process, we decided to do some of that work and work out whether it had to be graphene, or indeed in this area there was any benefit of exfoliating and size selecting down to near monolayers. So we use a technique called liquid cascade centrifugation, which is successive centrifugation steps. So we sediment the samples successively, collect the sediment as the sample, and take the supernatant onto the next centrifugation step. And that's smaller particles, thinner particles. They're inherently coupled for these systems. But we can have things that are large, bulky flakes, or we can select down to smaller but very few layer material. We characterize those typically with Raman, because we Raman mapping. So we map the Raman spectrum across the ensemble, and we get very good representation, which is more challenging with microscopic techniques. And we also see, as we increase the centrifugation speed or time, the Raman spectrum, particularly the 2D peak, that starts to look more symmetric, like the monolayer graphene. And when we do find few layers and monolayers in a lot of these dispersions at the small end. Okay, I need to probably speed up a little bit. We can also then, on all of these different size selective fractions, once we know the size, we can look at the surfactant content. So these are exfoliated in soap and water. It's notionally environmentally friendly processing. And we find that the samples that are smallest do indeed have more surfactant, more stabilizer, they have more surface area, so that's what we expect. And I'll come back to that later. So now that we've got lots of these materials, we can look at how the network conductivity, so the conductivity of a macroscopic film of these materials, depends on the nanosheet properties. Of course, as we make the nanosheets smaller, the resistance of the individual nanosheets goes down, or the length goes down, but the thickness goes down as well. But maybe most importantly, the junction resistance, which dominates the transport in these films, we would expect that also to increase, because we're making the overlap area between the sheets smaller, unless we're also changing something else about the system. So when we perform these measurements of two data sets here, one of them in red is when we do what I've called single centrifugation. So when we just skim the big stuff out and keep the successively smaller stuff, of course, we also retain all of the excess surfactant, and we see the conductivity drop off in the red. However, when we use this liquid cascade centrifugation technique, we're effectively washing, as a standard washing process people would use for the likes of, salt gel synthesis and this sort of thing. We remove all the excess, and we actually then start to see this emergent behavior where the conductivity continues to increase as we make the sheet smaller. This is counterintuitive, because the trend in the field has been typically bigger sheets are better, larger junction area, lower junction resistance, and you start to see the inherent properties of the materials. We just to put it in some context here. Here is a survey of some conductivities for various graphene materials processed in various ways in the literature. You can see the sort of, you take our materials in blue and green out, the general trend is bigger is better. What we're not seeing across these sort of isolated points rather than the systematic studies is that we're also likely changing the junction resistance, effectively the junction conductivity, and that's what's changing the conductivity trend in our networks. So we're actually starting to see some behavior where the smaller sheets are more conductive, not only than the biggest sheets, but they're more conductive than many other reports for graphene and for nanosheet networks in this area. So you don't have to use very big, thick graphene and compress it and do very circuitous things like some of the people over here do. You can actually have some inherent behavior that's associated with the processing that we do that allows us to make networks which we believe have improved transport. To understand that, how are we doing for time? 5 minutes-ish. Okay, no problem. I'll fly through the rest. So we started to think about why that might be the case. And then when we look at the different size fractions in SEM, for example, we find that not only are the big sheets sustaining larger pores because they're large sheets, they're rigid, the smaller sheets are flexible enough that they actually conform to each other. And so they reduce the porosity. There we go. We reduce the porosity, but in reducing the porosity, we also likely lower the junction resistance between the sheets. The samples are large enough and big enough that we can weigh them and do macroscopic porosity. We can measure the density before and after annealing the surfactant out and work out the full volume fraction composition of the samples. And we find that the smallest samples are more conductive, even though they have all this excess surfactant. So the takeaway there is that the surfactant is what helps us exfoliate the materials and change the mechanical rigidity. And when we change the mechanical rigidity, we change the junction resistance. We start to recover improved transport in these films that we expect for the materials. I'll sort of skip over this, but the conductivity increases by more than the graphene volume fraction increases. So we do expect the mobilities are increasing. We're working on measuring that. It's non-trivial for these systems because typically you have to use electrolytic gating, and the electrolyte can dope the system in itself. So it's more challenging to get very good, reliable, meaningful values for that. There are some models, however, emerging for junction resistance, and when we apply those, we find that in our smallest sheets, the junction resistances are expected to be among the lowest reported values for any nanosheet-based system. What else do I want to say? I'll just touch on this. Because we have high conductivity, we thought we would look at applications which require such. So thermoelectrics are materials which generate electrical energy from heat gradients. So you have a hot end and a cold end. And the figure of merit, ZT, requires high conductivity, but also high thermal voltage, Seebeck coefficient. We find that increases in our systems as well. That's likely a de-doping effect in the smaller sheets. The thermal conductivity on the bottom there remains mostly constant. So we actually see quite a stark increase in both the power factor and the power factor and the figure of merit ZT for these systems. So I'm not claiming this is an approach. I'm not claiming necessarily that this is an approach to make graphene thermoelectrics the best materials for thermoelectric devices. However, the approach allows us to increase the performance, improve the transport, while also de-doping the system. So we're not going in this sort of direction of metals. We're able to move through a couple of orders of magnitude of the thermoelectric figure of merit. So I'll just wrap up. This works for MOS2. We actually started making interfacial films using this Langmuir technique. So these films can be 20, 30 nanometers thick, but they still retain this performance enhancement. In fact, the performance enhancement doesn't matter what way you make them, as long as your sheets are small in the MOS2. We get about a factor of 1,000 rather than the, say, factor of 5 that we get by going to few layer graphene. When we go to few layer MOS2, we get a much starker increase because the junction resistance decrease that we get is much more significant. I think Natalia is going to talk after this about gas sensing in a more sort of by design way, but we also measure the gas sensing properties of some of these new MOS2 films made from the few layer material. We get quite low limits of detection to NO2, and particularly ammonia is the interesting one, down to 1 ppb. And just on a sort of lighter note for the end, we did this work with MPL and through various connections with local media. The interest that we had in real-time sensing, particularly for NH3, particularly for ammonia, it's one of the only pollutants that's not really going down over the last 20 years, and it's also one of the biggest contributors to particulate formation, to PM2.5 formation. So somehow we ended up, I don't know how I can control this video from here, not sure I can, ended up being asked for our opinions on BBC and ITV Southeast on the day that the ultra-low emission zone was expanded on ubiquitous gas sensing, ubiquitous air quality monitoring. Yeah, so we have interesting approaches to manipulate these materials. We can test them in relatively, we've not got the same slide here. We can test them, oh, here we go. Can I do that now? Yes, okay. Okay, so we'll forget the videos. We've got an interesting approach to play with these materials in quite large quantities. The small few layer nanosheets give us aligned networks with improved transport, and we're looking at that for thermoelectric gas sensing applications. And I'll just thank the people in the research group and collaborators who helped with some of the measurements. And thank you for your attention. I'll let you get to lunch.
So, bearing that paper.
Yes, it does to a degree. We don't believe they're doped by the choice of a particular surfactant. We don't believe that's the origin of the effect. We can anneal the surfactant out and we still see the same performance enhancement. Yeah, no, we'd like to move towards biodegradable surfactants and green surfactants and this kind of thing. It works with solvents as well, so there's not, it's not the underlying effect. Yeah. Yeah.
The question is, what surfactant and ultrasonication do you use?
The surfactant for most of that work is Triton-X 100. However, full disclosure, Triton-X 100 is on an EU list of surfactants no longer suitable for large-scale manufacture. So what I mentioned there, we're looking at alternatives and derivatives. The main reason we use that surfactant was because it's a liquid, so we can boil it off effectively and study the structure of the system after we remove the surfactant. But yeah, it works with others, and we're ultrasonication. We're using high-pressure homogenization, so that's the pilot-scale process that allows us to make large quantities. Whereas if we do ultrasonication, we're stuck with small batches, and we can't make half the measurements we want to make.
Thank you so much.
No problem. Thank you.